Hello, everyone. Welcome to EROSS DR online summer seminars. I'm Giancarlo Guizzardi, and I'm organizing this together with Enrico Franconi, Tiago Sales, and Claudine Moraes. EROSS is this series of talks with world-class figures in the area of conceptual modeling and adjacent areas like ontologies and cognitive science, linguistics, knowledge representation, and so on, and many others, philosophy, and so on. This is a series of events which is connected to the Bolzano Summer of Knowledge, which starts next month. So please check the information about the BOSC online, and also to this 4 decades tradition of the International Conference on Conceptual Modeling, which this year will happen online in the first week of November. So please also check the ER 2020 website for details. Also, there is a series of very interesting workshops and the whole tradition of the conference with keynotes and with a very, very interesting program. Last week, we had an amazing discussion with Melanie Mitchell on the role of common sense to artificial intelligence, right? So the discussion was also very centered around this idea that in order for us to achieve human level AI, for example, we would have to go beyond a pure numerical processing. And common sense plays a fundamental role there. And Melanie also defended that she thinks that what we have to develop in order to achieve this goal serves not only for reasoning, for common sense reasoning, but also for moral reasoning. And that's why, to make this connection very explicit, I choose the following quote to present our guest of today. It's not only important to provide accurate predictions, but also critical to provide reliable explanations to the underlying black box models making the predictions. If users and decision makers do not have faith in such predictive models, it's highly likely that they will reject its use. Furthermore, it's extremely risky to blindly accept and apply the results derived from black box models, which might lead to undesirable consequences or life-threatening outcomes in domains of high stake. I think this is a very nice quote to present our guest, and for many reasons. First, because it shows the excitement in this new class of applications, or the different applications of machine learning and predictive models. Also, it shows the concern with the social impact that these models and the systems, they can have a high social impact, and that's why we should really pay attention to their consequence. But it also let's say, hints to one direction of solution and showing the importance of understanding what is behind all this data and all these predictions. So the importance of real world semantics. And that's why we have today our guest talking about how to leverage artificial intelligence and machine learning and big data to create value. Our guest is Sudha Ram. She's an Endowed Professor of Management Information Systems, Entrepreneurship and Innovation at the University of Arizona. She's also the director of the INSITE Center for Business Intelligence and Analytics, among other things. She also participates in the Bio5 Institute, which is an interdisciplinary, very interesting institute doing research in life science. She has made seminal contributions to several areas, including enterprise data management, business intelligence, large-scale networks, and big data analytics, combining results from machine learning, statistical approach, ontologies, and conceptual modeling. She has received more than $60 million in research funding from organizations such as IBM, Intel, SAP, Ford, NIST, NSF, NASA, the CIA, the Office for Research and Development of the CIA, the US Army, and so on, and has served as a senior editor at the Information Systems Research, one of the top information systems journal. She's currently a senior editor at the Journal of the American Association of Information Systems, played a fundamental role in the Journal of Data Semantics for many years now, and She's also a founding editor of the Journal of Business Analytics, which is a new journal. Her research has been highlighted in several media outlets, including NPR and the New York Times. In 2013, she gave a very interesting TEDx talk entitled Creating a Smarter World with Big Data. She's also an American Association of Information Systems Fellow and an ER Fellow. And the list goes on. I'm extremely happy to have her here today. On a personal note, I think I met Sudha maybe more than 15 years ago. I think I was still a PhD student. And, you know, when I met her, I had this impression that she's a role model, one of these people that you want to be when you grow up. It's one of these people that can perfectly balance, show that scientific excellence and kindness go very well together. So I'm very happy to have her here. Sudha Ram, welcome to EROSS 2020.
Thank you so much, Giancarlo. That was a wonderful introduction. You're very kind. Good morning from the US. I'm in Tucson, Arizona, and good afternoon to everybody. I hope you can all hear me well and see my slides. Can everybody hear me well?
Yes, yes.
Okay, and you can also see my slides. Thank you very much for inviting me. It's such an honor and pleasure for me to be a presenter at EROSS 2020. I was so thrilled when Giancarlo invited me. He had originally invited me to Bolzano, and I was ready. I was packing my bags, and then COVID happened. So I'm equally delighted to be there virtually today. Today, I'm going to be talking about leveraging artificial intelligence and big data to create value. And so what I'm going to do today is provide an introduction to what I mean by big data, because sometimes there are some misconceptions about this term. And I'll talk about the most interesting parts of big data that we can actually leverage. You know, what makes it so interesting and why it's causing a paradigm shift. I'll also give you a very brief introduction to the kind of work I do. And then I'll go into some examples and talk about how we're currently leveraging. And then I'll end up with some latest work that I'm doing that's related to COVID-19. So let's spend a few minutes kind of thinking about what big data really means and why it's causing such a huge paradigm shift today. So if you think about it, we reached the zettabyte era many years ago now. It's almost like, I think 5 to 10 years ago, we reached the zettabyte era. And everybody said, you know, once we reach that, then that's it. We can't have any more names for big data because that's how much data there's going to be in the world, but we're still growing. And so we've reached the end of the English alphabet, and we don't really know what to call these bytes anymore because we've reached the end, which is Z. Fortunately, we're now regressing back to the dinosaur era where we're going to start calling them Bronto bytes and so on. So maybe at some point we'll have T-Rex bytes and things like that, which focus on the size of the data. But I think big data is so much more than size. When we think of something big, we think of the Great Wall of China, which is the only man-made object that can be seen from the moon, for example. But big data, the volume, of course, is a huge characteristic of big data. However, you know, a lot of people have a hard time putting a handle around what zettabytes mean, what petabytes mean, etc. When I started my career in 1985, there was no such thing as even a gigabyte. I think we had megabytes, we had bytes, and so on. But today, if we think about a zettabyte, you know, in terms of distances, you can think of the distance from the Earth to the moon. And if we stack up DVDs all the way from the Earth to the moon, that's about, and back, that's about a zettabyte of data. Or I showed you that picture of the Great Wall of China. And if I take a cup, you know, I'm holding a cup in my hand, If I stack these cups back to back, it'll cover the whole Great Wall of China, and that's about a zettabyte, if you want to think in terms of volume or area, things like that. However, the volume, the variety, the velocity, all of these V's are very alliterative, and people love to talk about these in terms of characteristics of big data. But I want to take you a little bit deeper than just these 5 V's. And I love these 5 V's. They sound great when you kind of spout them off. You have tons of data and there's come in variety and so on, but there's something more interesting about it. The first thing is, of course, as we all know, there are many, many different sources of data today in the world. We're generating data from every possible source. It's also coming at us at a very, very high speed. So for example, I kind of put 2 pictures side to side here just to give you a sense for how much data is being generated, not just internally by organizations, but also from external sources like social media, from Google searches. And if you think about what's happening just within a year, you can see on the left side a picture of what happens in an internet minute, and on the right side it's in 2020, so it's 2019 versus 2020. Let's take one example. In 2019, in 1 minute and 60 seconds, Netflix had about 700,000 hours of watched movies. In 2020, that increased to almost 800,000 hours. Google had 3.8 million search queries being issued every minute. And in 2019, just last year, and this year, there's even more, 4.1 million. And by now it must have gone up more because we're all sitting at home through Zoom or Microsoft Teams, and we're using Google more than ever. Similarly, you can see your favorite social media, whether it's Snapchat or Instagram, or apps being loaded from the Google Store or the App Store, etc. Number of texts sent. So this data is coming at us at a very high velocity. Interestingly enough, you'll see one big difference between 2019 and 2020, and that is the presence of TikTok down below on the right side of your screen. We don't know what's going to happen to TikTok in the United States, but certainly that's become very popular all over the world. So the point I'm trying to illustrate here is that there's a lot of data and it is being generated very, very fast. So we have now the ability to do a lot more with this high velocity of data. But why is there such a paradigm shift? Let's get down to it, because this still does not explain why this era of big data is so interesting for us. The first thing that I feel that's very interesting about big data is we now have the ability to convert into numbers or quantify so many things that we were not able to do before. And this is what is called the datafication phenomenon. What does that actually mean? This means that in the past, I knew that I lived 2 kilometers away from my office or 10 kilometers away from my office, or when I walked from my office to lunch in the student union or to a restaurant during the day when I'm working, I knew that I would have to walk for about 20 minutes, which is probably about a mile. But today, because of all the wearables I have, because of Google Maps and other ways to measure distance, I actually know that it takes about 2,200 steps when I walk from my office to lunch, and that's about a mile. I know, for example, when I sleep at night, how many times I turn over in my sleep, how many minutes of deep sleep I have, how many minutes of shallow sleep, how many minutes of rapid eye movement. I know what my heart rate was during every minute of that sleep. So what's happening is the whole world is getting datafied. Every piece of the phenomenon that interacts with us, anything that we interact with, everything is getting quantified and we now have the ability to start measuring a lot of things. A very simple example, the Samsung refrigerator that came out a few years ago, it uses this datafication phenomenon in a very interesting way. Used to be that when I would go weekly grocery shopping, I would buy my juice, the gallon of milk, etc., and put it in my fridge. And I would know that in about a week or a week and a half, I'm running out of it. And so I would have to go back to the grocery store. Today, that refrigerator can detect how many times you're opening it up, how many times you're taking out that milk gallon, and how much that milk gallon is getting utilized every time you take it out and use it. Similarly, when you put that 12-pack of beer in the fridge, and every time you take it out, the refrigerator can calculate your rate of consumption of beer. And using that information, it can send a message to your nearest grocery store with a list of things that need refilling. And so that inventory is delivered to your home automatically. And all you have to do is actually put it back into the fridge. And even that, perhaps you don't have to, because soon we're going to have robots that are going to do it for you. So this datafication phenomenon has become incredibly helpful to us in our daily life. So that's one aspect of this big data. But another aspect of it is that the line between the physical world and the digital world is slowly dissolving. How do we know that? Because we can see now things like self-driving cars, right? The car is a physical object. Driving is an activity. The car is able to sense other objects on the road, not navigate through them and navigate past them and not get into any accidents. When a self-driving car sees a person crossing the road, it knows it has to stop. And so all of these physical objects on the road are getting converted into digital objects, and those digital objects are being captured by data, which is quantified and being used for decision making. Another example of this line between the physical and the digital world dissolving is, I already talked about the Samsung refrigerator, where the physical inventory is then being converted into data, which is being transferred to your grocery store. I was a few months ago, I was walking on the Golden Gate Bridge in San Francisco, and I had an app on my phone. I had my GPS turned on, and that app was able to tell me, it was able to detect which part of the bridge I was located at that moment and what the view I was looking at was, and it was able to tell me that I was looking down on Alcatraz, which is that big former prison, and it gave me the whole history of Alcatraz. So my physical location was being translated into digital information, and that was being given to me. Similarly, when you go to the Louvre in France, you can have an app, and as you go through the museum, your app will sense where you are, and it's able to tell you that you're standing in front of a certain picture by Leonardo da Vinci or someone else, and it's able to give you the history. So these are all classic examples of how the line between the physical and the digital world are slowly dissolving because there are these sensors embedded in physical objects, and they can all communicate with each other using the same protocol that the internet uses, the IP protocol. And of course, part of that is now we have the ability to have these sensors do what is called the Internet of Things. So they are embedded in various objects, and soon we're expected to have more than 50 billion Internet of Things devices that are all connected to each other. This is not something new, it's just that the scale has become so much larger and the economics have reached a point where all of these things are generating a lot of data. So that's one aspect of big data. And here's the health Internet of Things. This is one of my favorites. I'm sure many of you wear a Fitbit, or you wear something that measures your blood pressure. It measures how well you're sleeping. At the University of Arizona, in the bioengineering school, they're working with the hospital here at the University of Arizona, and they've designed this device called the fall detector. You can wear, so people, when elderly people get admitted to hospitals, they wear this device, and every time they try to get up from the bed, this device is measuring 100 different variables about their stance, and it prevents and it detects if they're about to fall off and sends a signal to the nearest nurse's station so they can rush over to the room to prevent the person from falling, because falling is causing a lot of problems for elderly people. So there's a host of applications that this phenomenon of decreasing the gap between the physical and the digital world, that's helping us develop. But another aspect that I find particularly interesting about big data is no matter where this data comes from, whether it's from a wearable or it's coming from social media or it's being recorded through transactions happening like in Amazon or any store where you go purchase things, there are two very specific dimensions being recorded with each piece of data. And that is, every piece of data comes with a timestamp and a location, and a very precise location at that. So you know that even when your GPS is not turned on in your cell phone, location can still be recorded. Temporal, the timestamp is still being recorded. So when I make a post on Facebook or Instagram, when I watch a video on YouTube, when I do a search on Google, each one of those has a timestamp and a location. And that to me is perhaps the most interesting thing that we can leverage in order to create value from big data. And the fact is that now that we have this datafication phenomenon, the line between the physical and the digital world disappearing, and we have the timestamp and location, and we see massive digital traces being left by humans and inanimate objects, we can put these together, and that is what really helps us extract value or leverage machine learning methods to extract value from big data. And so to me, as a researcher in today's world, the entire world has become a laboratory for understanding the pulse of humanity. So what I'd like to do is talk a little bit about how do we actually leverage value from big data. And so it's kind of like the quest for the Holy Grail. The value of big data comes from being able to predict the future. And if we can predict it in a very granular way, then we can do some interventions to either prevent something bad from happening or to help something good happen faster, right? Like in healthcare, if we know someone is expected to move from stage 1 diabetes to stage 2 in a certain number of months, then perhaps we can do some interventions to make that a longer period of time or to prevent them from moving into stage 2. Similarly for cardiac problems or other chronic conditions. So today I'd like to give you some examples of how we can leverage big data to actually create value using machine learning. I started this research center at the University of Arizona several years ago. It's called INSITE. And our tagline is we want to create a smarter and better world using big data. And so a lot of the work we do is to either develop new machine learning methods or new quantitative methods. We use various kinds of machine learning as well as network science methods and make them scalable, and we do prediction modeling. And for the unique thing about our center is that we don't just develop these methods, we work on very interesting real world problems. So our challenge is to tackle real world problems and develop some methods, but in the process also do an empirical analysis to show that the problem is actually getting solved. We have a lot of areas we work in. Today, I'm going to give you an example from healthcare, from education, and then I'll end up by talking a little bit about my most current research on COVID-19. But the most interesting thing about what we do is we try to address problems that have social implications. So I know that many of you out there are thinking, when I'm talking about timestamps and locations, what about privacy? Aren't we actually violating people's privacy? And so I'll address that a little bit during my talk. And so the way I think about it is privacy is extremely important. We're very respectful of that. And sometimes there's a trade-off between capturing locations and timestamp and using it for social good versus kind of having complete privacy where you can't leverage any of that. And you'll see from the examples what I mean when I talk about them. So let's first so the way we do this is instead of, a lot of times in research, people have access to data sets and they sort of mine through it to solve a problem. What we do is we follow the scientific method, which is we identify a problem, define it, then we identify signals and data sets that would be useful to put together to integrate. And that's where a lot of my research in conceptual modeling came in, which was how do you integrate these various data sources? And I've sort of now moved on to doing this prediction modeling. We developed some data science-based methods that leverage machine learning and network science, and we solved the problem. But the key here is that data is out there, and we need to be able to repurpose it and use it in a way that can solve the problem. It's sort of like what Herbert Simon said. You observe a phenomenon, you define the problem, you collect the data, and then you end up solving the problem. So I'd like to briefly walk through the first two examples. The first one is about predicting emergency department visits using big data. The second one is very near and dear to my heart because I work in a public university, and I'll talk about predicting freshman retention, which is a challenge in the United States in most public universities. And then I'll wrap up with some very brief overview of the COVID-19 research we're doing here in my center. So just to kind of summarize, till now, we've talked about what big data really means. It's not just about volume or the V's. Most important is the spatial and temporal dimensions and the fact that we now have the ability to collect and repurpose data from various sources, and we have to decide which sources of data would be useful and whether there is enough signal in it, not noise, but how can we remove the noise and extract the signal so we're able to predict things for the future and do interventions. So this first example is a few years ago, I was on a panel with the CEO of a foundation that was focusing on chronic conditions. And I gave a talk on how we can leverage big data for healthcare. And this gentleman was very interested in seeing if we could do something about asthma. Why asthma? Asthma is one of the most common conditions, chronic conditions affecting people all over the world. You can see from these statistics, the one statistic that really stands out is the fact that every year there are about 3,500 deaths, of which at least 50% are avoidable. And the problem with these people is, the challenge with asthma is that people come into an emergency room with asthma exacerbation, and the emergency room is not prepared to deal with them. You can see from these stats again, 2 million ED visits every year. And there's lost productivity, 11 million missed school days. It's a problem that affects people of all age groups, from children to adults to even seniors. So this is a huge challenge. And so we worked with this hospital that was located in Dallas in Texas. And you can see from this map that this is a problem that's pretty prevalent in various parts of the United States. Um, a lot of the work was done in conjunction with several hospitals, and I would like to credit my former PhD student Wenli Zhang, the doctors we worked with, and it was funded in part by the Parkland Center for Clinical Innovation. Our goal here was to solve this problem I mentioned, which was, can we predict how many people will come into an ER, an emergency room, 24 to 48 hours in advance of their coming in? Can we predict how many people will come in with asthma-related complications? If we can do that, the ER can be better prepared, because currently the way things work is ER schedules are decided about 3 weeks in advance, and you don't really know who's going to come in. You can look at past data, but that doesn't tell you much. It's like tossing a coin. You can predict using forecasting techniques, but that's not very helpful. So when we started looking at this hospital's EHRs, or electronic health records, we found that just using past health records is not very helpful. We've got to do better than that. So the problem here, as you can see, it's not a new problem. It is a problem that's existed for many years. But now we have the ability to tackle it in a very different way and do predictions in a very different way. And so we said, why not leverage big data, which has spatial and temporal dimensions? Can we leverage social media data, environmental sensors, internet searches, things like that? You might ask, why internet searches? Well, because a few years ago, Google developed this tool called Google Flu Trends, where they were able to use keyword searches, and they were able to leverage the timestamp and location to predict how fast flu was spreading and where it was expected to spread. So the CDC, the Center for Disease Control, could figure out where the vaccines need to be rushed first so they could control the spread of flu. And so when we started thinking about asthma, we said, why not do something like that, but go beyond internet searches, maybe think about social media. And since this is asthma, we need to think about other kinds of data sources, such as environmental variables like levels of pollution in the air. And when you think about the environment, there's so many pollutants. There's carbon dioxide, carbon monoxide, nitrogen oxide, PM particulates that are less than 2.5 microns, PM10. There's tons and tons, levels of pollen, etc. Right? So what we decided was, we said, let's look for sources of data that we can, anonymize and still use. So we were in a quandary. Should we do this prediction at an individual level to say who will show up in an ER, or should we do it at a population level? I'm making this distinction because predicting at the individual level for ER visits, it's a very hard problem. In order to predict if one person, let's say John, is going to show up in an ER with asthma-related complications, I need a complete profile of John. I need not only John's EHR, I need to know his behavior, what he eats, where he spends his time, and that is perhaps very privacy invasive, and it's a hard problem to predict. So we said, let's do this prediction at a population level. So what we did here was we gathered data from social media, Twitter, and to our astonishment, we found people share all kinds of things on social media. Every time you go to your doctor, it's very episodic. You only go to your doctor when you're really sick. So when you have a very bad asthma problem, you might fix up an appointment and go see a doctor. Or you might say, I'm going to wait till it passes and I'm not going to go anywhere. Or I might go to the ER if I fall really sick. But the thing is that they post all kinds of things on social media. But there's one big challenge, which is if you want to repurpose social media data, and this data I'm showing you from Twitter, this data, you'll see on the left side are really true asthma tweets, whereas the right side, asthma is being used as a rhetoric. I think I'm having an asthma attack because you take my breath away. Or I was sitting in the bus next to a person who looked like Justin Bieber and I started to have an asthma attack. Or my chemistry exam was so tough, I thought I was going to have an asthma attack. So the first thing you have to do is we collected English tweets from all, various parts of the world. And many of these tweets come obviously with a location, not all, but they all come with a timestamp. So remember, our goal here is to predict how many people will show up in an ER with asthma-related complications. We're doing a population level prediction. So you can see we've just plotted these tweets without using a map of the world, and you can start to see all the English-speaking countries. A lot of them are in the US, and zooming in on the US, we used a bunch of keywords like asthma, inhaler. We used names of asthma medications, like Flonase, etc. And I won't show you this. I have an asthma stream that's coming in through Twitter. But we had to develop some natural language processing techniques, first of all, to distinguish which tweets were actually talking about asthma and which ones were just noise in the tweets. So things like rhetoric or advertisements for asthma drugs, or people even saying things like, I suffered from asthma when I was a kid 10 years ago, things like that. Those are not very useful. What we wanted were tweets that actually describe people's behavior. So we developed some NLP methods, and we were able to see that there is some sort of a lagged correlation between the ER visits and tweets. So people, it turns out, they tweet first before they go into the ER. Not so good for the person tweeting, but good for researchers like us because we can collect this data. Now here, we don't even need to know the identity of the person, but we do need to know where they're tweeting from and when they're tweeting. So again, we're leveraging that timestamp. So that's one set of data. The other set of data that's useful here is the Environmental Protection Agency in the United States has many, many different kinds of sensors that they've installed all over the US. And we were doing this prediction for one particular hospital in our initial model, which was located in the Dallas area. So we gathered not just the tweets from that area, but also the EPA data sets. And the interesting thing about these EPA data sets is while we get all kinds of data, there's still noise in that sometimes the sensors go down, so you have no data, there's missing data. Sometimes parts of the data are at certain frequency, like they measure rainfall, temperature changes, etc. at minute intervals, whereas they measure other things like levels of PM 2.5 at second intervals. So the frequency of measurement is very different. And so we decided to do this, convert everything to daily data, because our prediction goal was to be able to predict how many people were expected to visit an ER or an ED in the next 48 to 72 hours. And so these are some of the data sets you can find. And so we collected all of these. When we were first presenting this data, people said, why don't you use Google search data as well? So we threw that into our machine learning models. We didn't use any fancy machine learning methods. We used some decision trees, random forest techniques, and we were able to find that the things that were the data that were able to predict with 80% accuracy, which means 8 out of the 10 days, were able to predict how many people will show up in the ER, and we sort of bucketized the prediction into high, medium, and low, where we set threshold values. We can also do a continuous prediction with actual numbers, and we got about an 80% accuracy. Now, is that better than what we can do with past data? Yes, because if you look at ER visits, there's no pattern to predicting how many people will show up. And it's like I said, it's like tossing a coin. So heads means there'll be a certain number of people, tails a certain number of people. And so there's about a 50% accuracy. We're able to do much better. And we also found initially, when Giancarlo introduced me, he said, we want to think about explainability in AI. We were able to see that the tweets, the levels of carbon monoxide, nitrogen dioxide, and PM 2.5 are very useful in predicting how many people will show up in an ER. So why is this useful? Because by doing this prediction 48 to 72 hours in advance, we can publish surveillance maps to warn people that the number of visits is going to go up. It can be used to notify stakeholders in the community, like schools, etc. It can also be used to staff. The staffing decisions for an ER can be based on our prediction model. And now we've extended the study to 100 different hospitals in the US, and they are able to use our prediction on a regular basis to decide what sort of equipment they need to have, what sort of physicians they need to have, what sort of nurses they need to have on call for hospitals when they are predicted to have high number of visits. We could also use this to develop an app to do targeted patient interventions, to give them alerts and counseling for preventive methods. So these are very promising results for a non-communicable disease. So remember, earlier I talked about Google flu trends. Here, this is asthma, which is a non-infectious, non-contagious disease. Can we repeat this for other chronic conditions? I think we can probably do it for diabetes, because people share all kinds of things on social media about what they're eating, how much they're exercising, etc. I don't think this will work for cardiac problems. I do not see people tweeting about cardiac problems before being rushed to the emergency room. So I think, yes, it'll work for certain chronic conditions, but for others, it may not work that well. In fact, we're experimenting with diabetes, and that prediction seems to be working quite well, not as well as asthma, with about 75% accuracy. So that's one example where I think the key point that I wanted to bring out was we defined a problem, we decided what the prediction goal was going to be, and then we collected and repurposed data that would be useful. I also wanted to tell you, before I go into this next example very briefly, is that Google search data was not helpful in our prediction. Why? Because when people search for things in Google, it's not necessarily because it's affecting them. It's because they're interested in finding out things. So for example, when there was that Ebola virus scare, or now that we're in the COVID pandemic, a lot of times we go search for COVID-19 symptoms or COVID-19 deaths or hospitalizations, not necessarily because we're suffering from that problem. It's because we want to be kept informed of things related to that virus or the pandemic. And whereas social media, people actually post things that can help us extract their behavior, what they eat, their lifestyle, things like that. And those are the kinds of signals we need to be able to make this prediction. So now let's move on to the second example, and I'm going to quickly go through this, which is when we started working on research like this, the university that I work at, the University of Arizona, is a very large public university. We have about 40 to 45,000 students. And one of the biggest challenges in the United States with public universities like ours is that we have a mandate to bring students in from our state. These are called in-state students, and it is our mandate to make sure they actually finish their undergraduate or four-year degree. Sometimes they take 4 years, sometimes 3 years, sometimes 5, 6 years. But the idea is to have good graduation rates, because I don't have to explain to a lot of people. I'm sure in the audience we have lots of academics and students. We all understand the value of education, not only personally, but also economically. And from a university perspective, graduation rates are very important because they determine the level of federal funding that's given to the university. So one of the biggest challenges with public universities in the United States, and I think across the world, is student retention. At the University of Arizona, we have about an 80% retention rate. That means every year we bring in about 10,000 undergraduates into our 4-year program, and 2,000 of them drop out at the end of the first year. And they're not necessarily dropping out because of not doing academically, they're not doing well. There are a lot of social science theories that have tried to tackle this problem. And this is, again, not a new problem, but it's a problem that's been around for years and years. There are universities in the southern part of the United States where retention rate is as low as 50%. That means 1 in 2 students is dropping out. We're much better at the University of Arizona, but this is still a societal challenge. And like I said, the idea of our research center is to leverage big data to tackle important problems that have social implications. So we said, why not look at this problem of student retention from a new perspective? Let's put a new lens on it and look through it. So we looked at social science theories, and a lot of these theories say that when students come into a very large university like ours, and a lot of public universities are very large. University of Texas, for example, has about 60,000 students. Ohio State University has 70,000 students. One of the big challenges is that students don't establish good social interactions, and they don't establish a regular routine, and they get lost on campus. They feel very uncomfortable, and they eventually drop off. And so the grade point average sometimes does not indicate that they're having trouble at the university. Sometimes it does, but it's a lagging indicator. It's a symptom. It's not really the underlying cause. So if we want to predict that students are going to finish the first year, or if they're going to drop out, how do we do this prediction? Well, one way is to measure their social interactions and then to see if they've established a regular routine. But the question becomes, how do you do that? And so when we were discussing this problem, somebody came up with the solution, and they said, oh, I know what we can do. We can embed a chip in every student and see if they're interacting with each other. And I said, that's way out of the question. That's hugely privacy invasive. And by the way, I'm just joking, right? Please don't take that seriously. We obviously cannot do that. So how can we solve this problem? This is when we came up with our goal, which is here we're going to do an individual level prediction, unlike the previous example where we were doing a population level prediction. There we were predicting how many people would show up in an ER. Here we are predicting which individual freshman is likely to graduate. But the key here is, just like in the previous case, we wanted to predict 48 to 72 hours in advance, or maybe a week in advance. Here, we want to predict about 10 to 12 weeks into the first semester. Why that? Because when we did our focus group interviews with students when they drop out, we found that most students decide to drop out not after the first semester, but their decision itself is made about 10 to 12 weeks into the first semester. So timeliness of the prediction is very, very important. In fact, I can't underscore enough the importance of the timeliness of this prediction. A prediction is only useful if you can predict with enough time left so that you can do some interventions. And this is a classic example of wanting to predict before the end of the first year, before the end of the first semester even, which means we don't want to use their GPA because the GPA only comes out 18 weeks after the semester starts, because our semester is 16 weeks, then we have exams and so on. So that's the big challenge here. So what do? Well, we said we actually have some spatiotemporal data because every student on campus uses something called a smart card or a cat card. We are the Arizona Wildcats, and so we got permission from the IRB to get anonymized smart card data where we remove their identities. And we said we'll leverage the spatial temporal data because this card is used in many places on campus. And so we collected first data for a year, and then we expanded it to other years. We did this. So our strategy is always to sort of do this on a small basis for a short time frame and then expand. Just like in the previous case, we started the experiment with one hospital, expanded to 100 hospitals. Here we said, let's try to do this prediction with a single year, and then we'll collect data for multiple years. And so now we've expanded to 3 or 4 different years. So this cat card is actually used in about 500 different places on campus, like, when they enter their dorms, when they use vending machines, when they go into a lab, when they use the library, when they go eat somewhere, things like that. So using this data, and you can also see from here that at the time we had about 7,000 full-time registered freshmen, about 6,500 left after removing international students. And then you can see about 13% dropout at the end of the spring semester, but about 5% dropout at the end of the fall semester, or 7%. But really you want to predict these 20% before the fall semester ends, because that's the first semester. So what we did was, this is where network science comes in very useful. We were able to construct networks of interaction among people based on if they show up in the same place at the same time within a specific time window often enough. Using threshold values, we build these networks. On the left-hand side, we see people's interactions in different places at a certain time. On the right-hand side, we see it at other times. Here you see in this picture, I'm just showing you visually, but we have extracted quantitative metrics out of these networks. On the left-hand side, you see places frequented by economics students. On the right-hand side, you see places frequented by the sciences students. Of course, the numbers are different, so you have to normalize. So based on this, we were able to extract a lot of signals about how frequently do people interact, how is their interaction changing over time. We even built a model that is able to predict if they've established a regular routine and how predictable their routine has become week to week. And so using these signals, quantitative signals, we were now able to predict with 90% recall, which means out of the 2,000 students that drop out at the end of the first year, by the end of the 10th week, we are able to predict 90% of them. And then we looked at the people that we predicted inaccurately as not dropping out. We found that eventually about 5% of those students drop out by the end of their second, third, or fourth year. So these social interactions and regularity of routine metrics that we extract are actually helpful in doing very early predictions for us. So how can this be used? This can be used in different ways. This can be used to actually put in interventions. So now that we know which student is likely to drop out, we're working with the student retention office to do things like having the counselors talk to these students to find out what their challenges are. And again, we've opened up the black box to see if it's the regularity of routine features or the social interaction features. And now we've started to institute certain things like socialization in the dorms, having people, teaching people how to deal with a large campus, how to establish a regular routine so they start to settle down. That makes them feel more comfortable. I don't have any studies finished yet on whether these interventions are helpful, but we do know that the prediction itself is quite accurate. The question also becomes, will we ever get to 100% accuracy? I'm not sure we can ever get to 100% accuracy, but at least we're able to get to 90% recall. So that's another example. Now I have about 5 minutes left, so I'm going to briefly summarize some of my latest projects, which is on as a public university, our biggest challenge in today's pandemic, I'm sure it's true of your universities as well, in your organizations, is re-entry. Our semester is supposed to start next week, and we've been working furiously over the last 4 months since March or April to figure out how to safely reopen the university. And so one of the things we've done, and we've had lots of efforts going on, but I'm involved in 2 of those efforts. The first one is called contact tracing. What is contact tracing? If someone tests positive for COVID, we want to be able to identify that person, or they want to be able to self-identify, and then there is a contact tracing effort which will call these people and ask them if they remember who else they came in contact with. Sometimes people know the people they came in contact with, and so they can inform those people. Other times they don't. So there are some digital methods that can be used. And we're actually adopting a mobile app called COVID Watch, which is based on the Google Apple exposure notification API that Google and Apple have come out with. The way this exposure notification app works is it's completely private. What does that mean? That means that we install the app on our phone, whether it's an Android phone or an iOS, an Apple phone, and you turn on your Bluetooth, and these apps on the phones communicate with each other without tracking your location. So what they do, these Bluetooth signals do, is they use the signal attenuation to predict how close you are and how much time you've come in contact with each other. When someone tests positive for COVID, they can enter that into the app, and the app can then identify who are the other people, other phones in the vicinity who had more than a certain threshold of time of exposure. And it can notify those phones, and those phones will pop up. So if I get a notification on my phone, I know that at some point I was close to somebody who's been tested positive. And so the app might tell me to quarantine or to watch for symptoms or to go get tested or take some other intervention. So it's a very private way of exposure notification. There's also manual contact tracing. Is if someone chooses to report to the manual contact tracing team voluntarily, they can call you up and walk you through an interview to ask you where you went and who else you came in contact with. Now, of course, some people choose not to use the digital app. They might choose not to do anything, in which case you can't really do any interventions. But if they choose to report their positive test, then manual contact tracing will be in touch with you. But one of the challenges with contact tracing is we don't always remember who we came in contact with. And so what we've designed is using Wi-Fi logs, we've designed, so this is the app I was talking about just a minute ago. This is the memory jogger we've designed using Wi-Fi logs. So again, remember I talked about the temporal and spatial aspects and repurposing data. So we said, if people are on campus, how can we jog their memory about where they were and potentially who they could have come in contact with? Again, we don't want to track who, the people that they're talking to. Rather, we want to give them the ability to remember and jog their memory. So we harness the Wi-Fi logs. On campus, we have 3 different Wi-Fi networks. We have the regular Wi-Fi, we have Wi-Fi guest, and we have EduRoam, which I think many of you have as well. And there are lots of these logs that are being tracked for security reasons. So we anonymize these logs and we generate, you see this map in front of you. This is actually my map on a certain date when I was on campus. And it shows all the different buildings where I spent time. And the darker the color, the more time I spent. So I can actually move this, the timeline on top to see where I went on campus, and potentially when I talk to a manual contact tracer, it'll help jog my memory to remember who else was there. And that way they can, either I can choose to contact that person or I can give them the name and they can contact that person. So again, it's a privacy preserving way to be able to help in contact tracing. So that's one of the things we've developed. And the other thing we're doing is currently this week we're predicted to have anywhere from about 6,000 to 10,000 people coming back to campus. Not all our classes are going to be on ground. Some of them are going to be online or hybrid. And so what we needed was some mechanism for people to understand how crowded a location is, whether they should be going for lunch to the student union or they should wait for a while. We also wanted to track if there are certain parts of the campus that are getting very crowded so that we can put up signage or help dissipate crowds. Because we know that certain universities opened and they closed down because certain places became too crowded, and the more crowded a space, the more likely it is for the virus to spread. So what we're doing is we have designed a Wi-Fi log-based dashboard where we again harness the timestamp and location. And I'm showing you a picture of the dashboard here. On the right side, you can see a map of various buildings on campus. I can choose the date. So this happens in real time. So if I decide that I want to go to the library to study, I can use this. I can log in using my private net ID at the University of Arizona, and I can pick the next half hour, and we have a prediction model that runs in the background that will tell you how crowded a place is likely to be in the next 20 to 30 minutes. You can also look at currently how crowded it is because we have access to the Wi-Fi logs. So here this map shows from 8 to 9 a.m. on this particular day, how crowded were various buildings, what were the top 10 buildings in terms of crowds, and which times of the day it's likely to be crowded on a particular day of the week or a day of the month, and so on. So that way, different stakeholders can use these. We can also go into a building and visualize how crowded that building is likely to be or how it is at this present point in time. And so our stakeholders range from individual students to people who need to make decisions about how to dissipate crowds or how to distribute people between various buildings. And then the last project we're working on is we're trying to compare the various contact tracing methods. I just mentioned the app, I mentioned the manual contact tracing, I mentioned the Wi-Fi log-based memory jogger. So we're developing some methods to figure out how do these approaches differ in their outcomes, like timeliness of tracing contacts, the comprehensiveness by which we can trace contacts, etc., and how quickly do they actually help us cover the campus. How do these methods complement each other? which method helps in preserving privacy, what are people's attitudes towards these various methods, how acceptable are these methods to the community. And so hopefully once we have done this study, we'll have a very nice understanding of what's a good effective path to deploy comprehensive contact tracing. So those are some examples. So I just want to summarize kind of the learning based on all of these different projects. Remember, I started out the theme being how do we leverage big data and AI to solve interesting problems, right? And so some of the things we've learned in the process is that you don't always need a very complex algorithm. You don't need causality for prediction. If you have some theories, you can use that to set up your prediction model. But prediction is different from causality. What level of accuracy is good? In the real world, 100% accuracy is simply not possible. Sometimes even 80% accuracy is very good. Working with your stakeholders to define your problem is important. And of course, we do all of this research to help generate training for the next generation of scientists, end users, etc. But some general lessons we've learned are you want to focus on defining the problem carefully because this is a prediction problem. You have to think about what are you predicting, and you have to think about, think out of the box when you're thinking of a solution. So rather than leveraging a single very large data set, you think of data sets where the granularity of data is very detailed. You have locations, you have temporal features. How do I anonymize it? How do I preserve privacy on the one hand? And at the same time, I'm able to make a very good detailed level prediction. And how do we repurpose and combine different types of data? And you'll find ideally, we would have liked to have signals of all kinds. Like in the asthma case, we would have loved to get access to people's text messages to each other, but that's simply not possible. And it doesn't preserve privacy. So sometimes you have to sort of think about the trade-offs you're making. And then you can leverage various kinds of data. And then finally, I want to say that often when you're repurposing data, there's a lot of noise. And if you end up using noisy data, you're not going to get very good predictions. So understanding what the noise is and how to remove it is hugely important. So I'm just going to stop here and say that we live in a world where we're just flooded with data. And there's predictions, but that by this year, the number of data science jobs in the US alone will exceed 500,000. And in fact, this prediction has not only come true, but it's been exceeded. There's a huge shortage of people who can do this kind of work. So this is an excellent field to get into. And I have to say, I got into this only because of my training in conceptual modeling, which kind of helps me think in abstracted ways about problem solving. And so in conclusion, I want to say this is a very exciting era for us. Big data, I hope I've given you a good insight into why it's causing such a paradigm shift and how there's a lot of hidden value. You can actually use big data for doing a lot of social good. So let me stop here and ask if you have any questions and open it up for discussion.